Ladies and gentlemen, please take your seats. Our program is about to begin. أيها السيدات والسادة، سيبدأ البرنامج بعد قليل، لذا نرجو منكم التكرم بالجلوس في مقاعدكم.
Ladies and gentlemen, please silence your phones. Our program is about to begin.
Good afternoon, everybody. Welcome to another day of WEP, of digital adventure, and I hope you had a good lunch earlier. Just a kind reminder, food and drink are not allowed inside the hall, so if you can finish your lunch before you come in, we would appreciate it. And also one more thing, after the session, there will be the Q&A session, and as you've seen from the past lectures, there are 2 mics on either side of the stage, and just form a line there to ask your question, and the lecturer will be happy to answer it. Today's lecture is going to be moderated by Professor Jin Gao. Professor Jin is a full professor here at KAUST and the chair of Computer Science Program in the SEMSI division of KAUST. He's also the director of the Computational Bioscience Research Center, CBRC, and the deputy director of the Smart Health Initiative, SHI, at KAUST. And now, without further ado, Professor Jin Gao.
Thank you for the introduction, which I believe I probably don't need. So you should have known me unless you didn't attend the opening night, which means you will most likely fail the WEP course. So it is my great honor and pleasure to introduce the keynote speaker, Professor Cheng-Wei Qiu. And since I'm the chair of WEP and I'm moderating this session, you know how important Professor Qiu is. So Professor Qiu is currently Associate Professor and Dean's Chair in College of Design and Engineering at National University of Singapore in US. For those of you who know about the history of KAUST, you know KAUST has a lot of connections and collaborations with the US. And I was also just informed by Professor Qiu that his promotion to full professor has already been approved and yet to be announced. So congratulations to him. He was also appointed IEEE Photonics Society Distinguished Lecturer 2024. And he is the recipient of numerous awards. I literally mean numerous, because if I just read along the list, that will probably take the next 30 minutes. So just to give you a few examples, he was an elected fellow of APS, a fellow of Optica, a fellow of SPI, and a fellow of the Electromagnetics Academy, US. He received President's Science Award last year, the highest science accolade in Singapore. And he was also elected fellow of Asian Academy of Engineering and Technology. He is well known for his research in structured light and interface and has published almost 500 research articles. He was highly cited scholar for the past 5 consecutive years by Web of Science. and he has been serving as associate editor for various prestigious journals and serves in the editorial advisory board for Laser and Photonics Review, Advanced Optical Materials, and ACS Photonics. So it is our great pleasure to have Professor Qiu here today to talk about his most recent research. Without further ado, let's welcome Professor Qiu.
All right, so first of all, I would like to thank Professor Gao's introduction, as well as the kind invitation by WEP program to have me here. And my name is Cheng-Wei Qiu, and in short, you can just remember me in a short form, CW, or you call it Clever Wave. All right, so I'm going to talk about digital intelligent metasurfaces. It's simply because my research is in optical metasurface per se, and everybody has to be, intelligent somehow, right? We love to be intelligent. We love intelligent stuff. So the third thing is I was told that now Gao's research has to be aligned with national priority. So my talk needs to be aligned with WEP priority. So I put digital in front. That actually confines what I can present. So, so today is just part of my research activities back in Singapore. All right, so speaking of digital, I think that's what should be in my wife's mind, all right? Especially the digital commerce, the Alibaba, Taobao, Amazon, whatever. And this is basically what it in our mind, this 1 and 0 in electronic world. But I have to say that the digital in my mind, especially dealing with waves and lights, are slightly different from the traditional concept. So basically, I would start from something high above, and this is how 1 and 0 is going to work. I think that's going to be some problem in the... It doesn't move. I don't know how to solve these technical issues. Okay, so sorry that I clipped some cutting the clips from a Chinese version, so you can ignore all the Chinese. All right, I will bring your attention to the video later on.
并为我们揭开了一幅又一幅神秘莫测的宇宙画卷。而旅行者号计算机
good
最惊艳的地方
for Chinese
就是其内存了。每台
So
计
this
算
is
机
for
都
the
有
RAM,
自己的镀线存储器，它们以最基本的形式。
This is how I was inspired because nowadays you have like current and you have metal wires. So you can basically send in the current and then you get magnetic field. So you can basically switch the current's direction to switch the magnetic field direction. So you can serve that as 1 and 0. All right, so this is basically a very building block of how you can design binary metasurfaces. But of course, metasurface dealing with light. So basically, you can see the center of the picture. So light has a lot of interesting degree of freedom, like amplitude. So you can call the amplitude to be binary or to be digital, because you can apply an amplitude and you can apply 0 amplitude, right? Like a bright and dark. And also, you have this kind of direction, we call it polarization. So basically, you can control the polarization to be like an orthogonal, like a horizontal linear, a horizontal vertical circular polarization, spin up and spin down. So you have a set of 1 and 0 degree of freedom to play with, as well as especially the phase, the phi, the term in the bracket. So I would elaborate how the phase could be binary, could be digital as well. So to start from, basically, in the old days, when we deal with light, no matter it to be a lens, it to be hologram, it to be like your glasses, it's always curved and bark compared to the wavelengths. So basically now, everything can be flat, can be just fabricated on the surface, and it is ultra thin. So everything can be done in the surface. So you can using FIB or electron beam lithography to pattern your metasurfaces to serve as like a counterpart, ultra thin counterpart of your traditional optical setup, so that you can manipulate all the amplitude, phase, polarization, wavelengths, angular momentum, and pulse shaping. So I know you are not in my field, so basically I want to just give you a sense of how the metasurfaces are progressing. So in short, basically, I think like Professor Gao is more interested in biomedical application, and national-wise, we are all crazy about quantum application. And for some other applications like computational electromagnetics for the health monitoring, so we have a computational information metasurfaces. And actually, one of my major interests nowadays in my group now is in hybridization with 2D materials. But I don't talk about this one this time. Maybe we have next time to share my research activities there. But the key message is below. So Metasurface provides a playground of 0 and 1, and yet it can go beyond that. Okay, so first thing first, let's talk about amplitude, because that's the easiest one to understand 0 and 1, right? Because you have bright and dark that serve as like a 1 and 0. So you can basically mingle with all sorts of 1 and 0 in a surface. And you can put 0 and 1 in the position you want, and when the light passes through, it interferes. So I give one very public or very easy to understand example, the hologram. So for example, I have a metal surface, and I just punch holes. Where I punch, it's kind of like a transparent, right? The light can pass. If I don't punch the holes, that blocks the light. So you can consider it's like a sieve, all right? And when the light passes through, you can design everything you want. Like you can show a kind of like a bird hologram, all right? And it's in nanoscale, and it solves a lot of traditional holograms issue, like a twin image issue. So, but what is interesting about that? And we feel like now we combine with intelligent algorithm so that we can assign a hole, which is like a 1, if I call 1 to be transparent, right, with the light passing through. So the radius of the hole and where it is all about the algorithm to decide. So right now, we have to target on one optical application, that is the imaging. As you know, imaging usually is ruled by diffraction limit equation, right? So it is, roughly speaking, it's lambda over 2. So meaning if you send the light, and when it focuses, the focal spot, the half maximum width cannot exceed lambda, go below lambda over 2. So in this case, basically, you can see on your right, there's a lot of SEM figures showing these holes. It's not a ring, it's just holes because of the contrast issue. And you see the holes, the size of the holes are actually different along the radial direction. So we basically designed this using algorithm, and the purpose is we want to focus the light down below the diffraction limit. So I use red light, which is 633 nanometers in terms of wavelengths, but the spot is only 200 nanometers. So it's roughly lambda over 3 point something, right? So it is so-called super oscillatory focusing. So this is good because now you can scan a lot of things very tiny with tiny features. While you can use your normal focusing lens, you cannot resolve it. But of course, I mean, if you punch holes and not punch holes, this kind of combination, you can always write a certain rings and not writing rings to block light or let light pass. So we do this is simply because we are doing this because of this guy. Yes, if you really look at this one, if you use this focus light to serve as your imaging scanning system, it has problem because you have a sideband. That's actually adversary. So we want to kick out this kind of sideband. However, if you want to kick out the sideband, it falls back into the traditional setup of the diffraction limit equation. You cannot achieve 200 nanometer in terms of the resolution. So somewhere we have to, accept the reality and bend our knees. So how we bend it? I mean, the trade-off is actually, if consider this kind of traditional area spot and also our super oscillatory lens. I mean, this side and the other side. Actually, that's a regime. So you can approach to the regime boundary that you don't excite this kind of strong sideband, but while your center spot is almost the same. So we call it supercritical lens. It's just about to get worse, but then you stop where you are. So basically now you can consider we can have a single spot in the middle, which is 165 nanometers. But of course, we choose blue light because the wavelength is shorter, so the width is shorter. It's good for resolving the nano features. So you can clearly see that using this kind of focusing spot, we can actually scan and resolve this kind of holes with 65 nanometers in between. All right, so this is good for super resolution imaging. And second thing is, I think when we talk about 0 and 1s in amplitude, it can go beyond so-called definition of a two-state or binary narrative. Actually, we can consider once you have a surface, if you use light, when your light address a point, a position, you can consider it's like a 1. If you don't address a point, it's just like a 0. And actually, when you address it, you can also control the light power intensity to drive the material morphology. So that's how we do it. So you can see that now if you have a laser, and if you scan the laser's direction using different power density, you can actually drive the polymer into a certain direction. So you can grow something out of a flat surface. So we can show that you can grow a pillar, and the pillar can be tilted. All right, so I think, of course, the color is actually depending on how you pattern this kind of pillars, and the periodicity will give you a structured color. But anyway, let me just using videos to show. It is stuck again. Yeah, I think probably I need some help to play the video, but yeah, it's played. So you can see that this is actually a video recorded in the process. When you do the laser scanning, asymmetric scanning, heating, then the pillar is tilted, and you can basically, design a certain like a trapping out of a surface that you can trap using 4 pillars and trap a particle in the middle. To get it fixed there. And of course, we can further design something else, like a smart hand, like our hand, and we use polymer, especially in the joint area. But in order to accumulate or expedite the heating process, we actually immerse a lot of nanoparticles in this area. All right. So usually the light hits on here, then it becomes hot, then it expands. But we use certain special materials. And at certain temperature window, they actually, when it gets hotter, it shrinks. So inside, it shrinks. Outside, it expands. So it facilitates the bending. So you can clearly see that we can use light to address point by point to control the holding of your hand. This is actually like a polymer hand. All right, so I think roughly it's like this. And of course, we want to make it like biomimetic motors or make things more connected to the human nature. So using light. So we basically design a few things using the same methodology. And we can design the fly trap using light to control it. And we also design a so-called moving spider, paper spider. But of course, we combine the graphene oxide inside and also put certain nanoparticles to expedite the heating process. And again, I tried to use my video to help. Hope it played. So this is actually what we fabricated, actually printed using the DVD writer stuff. And then this is actually not a real spider. It's just like a paper spider. Then if you a normal laser pen to drive it, of course, it needs certain artificial intelligence to how to move around the pen, but it's not that difficult. So your brain can be trained, along the way. So you know how you move it. This one, because it contracts, expand, basically it can move along a certain trajectory. All right. So the second thing is about amplitude is we try to do something that is not so boring to us, and out of my Metasurface work, because I feel this example may interest the general audience. So basically, this is a Da Vinci's plot, right? The very famous painting. And you can see that basically all the ratios follow a so-called golden ratio, which is 0.618, right? And you can Google it. That's the so-called golden ratio. So you may wonder how the golden ratio could help. What we can drive from this one. All right, so it goes back to the bird hologram, if you still recall. Because we punch holes, the light pass through. You don't punch holes, you don't pass through. Then this is about the art of punching holes, because we want to punch in holes using this kind of golden ratio. And that is actually inspired from, when I look at this sample, it reminds me that when I look at this kind of sunflower plant, and sometimes you see this kind of Fibonacci array stuff. So this is basically, this is a video. I will, if stuff can help me to play it. Now, just let it run. I will let you know what it means. So basically, if I consider the yellow dot is where you punch a hole, all right? So half means you punch the first hole on the right of the cross, then you punch another hole with pi angle difference. Then you increase your radius a little bit, then you punch another hole, and punch another hole, and punch another hole. So the first figure shows you punch an array of holes like this. Now, if you rotate your second hole, punch the first hole, then second is 36 degrees away from that, and then 72 degrees, so on and so forth. You punch 10 holes one round, and get back, you move in the distance away a little bit, and punch the next round, and punch the next round. So you got the second figure. And if you consider 3/10, then that's how it looks like. So this is quite normal. It doesn't give you anything special. So you can see that now if I just take certain clips out of the video, you will see that now if this figure is around 0.618, that's this third quadrant figure shows. That's interesting. That's actually very interesting because nowadays you see this kind of spiral. You have a very well-defined spiral, but one spiral with the neighboring spiral. If, let's say, you have a hole here along this spiral, and you have another spiral here, but this hole, and another spiral, this hole, you form kind of like a secondary spiral. So one picture actually gives you multiple functions. So that's why we take this picture as example. So basically, we fabricate it, punching holes still, and you can clearly see that now you have different kind of spiral fashion. So one typical design, it actually have 4 typical spiral patterns. And if you measure it in the imaging plane, basically it gives you 4 different kind of topological charge. It's so-called orbital angular momentum being. All right. So this is how these kind of mathematics can help in punching holes and play with 0 and 1s. The second thing that I want to talk about is the polarization. So polarization, sometimes it's hard. It's slightly harder to imagine what is 0 and 1s. So let me redefine the polarization, because all we care is polarization state. And usually we consider 2 orthogonal polarizations. So you can use 0 and 1 to stand for this kind of orthogonal polarization states, because with these 2 guys, you can construct everything in the middle, all right? So it's more like a fundamental basis. And when we talk about polarization of the light, actually we need to start from the quantum state of the electrons. So you have electrons, you have spin up and spin down, right? The spin of the electrons. But photons, they don't have this kind of spin. So this is actually, let me just convert it, all right? It just turned 90 degrees. So if we consider propagation wave, if the electric field tip moves around the time like this or like the other one, we call the light spin. So the light still have spin up and spin down, corresponding to right circular polarization and left circular polarization. So this is how it looks like, right circular polarization and left circular polarization. It makes you feel dizzy, right? But if you look at this kind of the very thick arrows rotating in the center plane, it follows a certain anti-clockwise. Then this one is clockwise. And if you compare with the electron spin, it exactly follows a certain analog. All right, so that's why we call it light spin. And they have defined like a spin +1 and spin -1. And that serves the fundamental basis. So out of this 2-degree freedom, you can construct anything, linear polarization, elliptical polarization, and out of the linear polarization, you can construct the other set of orthogonal polarization bases, like a radial polarization and azimuthal polarization, so on and so forth. So it has a very huge diversity and degree freedom you can play with. And this kind of things, you can use this kind of circular polarizations to design the meta-hologram using Metasurface. As you can see, you just turn the nanobar, the gold bar, and you send the laser to it. And at the imaging plane, you can see this kind of three-dimensional hologram, like an airplane there. And of course, we want to make it more intelligent, right? As I said, intelligent metasurface. So we want to make sure that we want to achieve a tunable metasurface, at least somehow, more intelligent than the static version. So usually we have to combine this kind of metasurface using different kind of materials per se. One is gold, one is magnesium, and the other one is gold. All right. So we can basically using hydrogen and oxygen to drive it between two states. And basically, you can clearly see that now we can design the sample, and it shows a hologram of Y. And then if you do the hydrogen, basically hydrogen will merge with the magnesium, becomes MgH2. Then this material changes property. So overall, the response, the polarization state will change, and then this hologram becomes N. So you can design this one using different functionalities, so you can change it so that the focal spot out of the same metasurface, after you drive between hydrogen and oxygen chambers, the focal spot is changing. All right. So you can design a lot of dynamic, tunable metasurface or meta lens out of this mechanism. And this is a picture that doesn't help. Doesn't run. But anyway, you can use your imagination to show that basically the Y is shifted to N in real time. All right, yeah, it works. Thanks for the hero behind the screen. So this is basically to show you that it can basically in situ change the hologram. All right, so basically you can see that now. Let's say if you look at the figure A, for example, all right? Just look at figure A. Now, the fundamental issue is, the fundamental principle is when you rotate this gold bar, if you, let's say the theta changes from 0 degree to 90 degrees, and the phase actually changes 180 degrees. So it means that the single bar actually contains a lot of degree freedom to play with. If you rotate by 1 degree, when the light passes through, you have a certain geometrical phase, which is 2 degrees. If you send 45 degrees, the outcoming light carries 90 degrees, so on and so forth. So there's always a double, a 2 times difference. And I know it's a little bit difficult to understand if you are not familiar with optics. So let me put it in this way. Imagine you have a very unintelligent creature. They don't know how to move around, all right? They just follow a different direction, and they move in this way, from North Pole to the South Pole, and then go around. So essentially, it goes back to the original state. So in terms of polarization, it still becomes itself at the very beginning. But you see a dashed head there, that's where it comes back, the position where it comes back, right? So it gains a certain phase. That phase is exactly the 2 times of the solid angle of your sphere, if you consider that a sphere. So that's the geometrical phase, all right? So basically, if you consider polarization, if you consider you have 2 linear polarizations, stand for the blue arrow and the red arrow. If you move from the point A to point B, then point B to point C, then point C to back to point A, it changes, the direction changes. So you can consider that it gains a geometrical phase of 180 degrees. So it's more like a, now, let's say I was here 10 years ago. Now I'm back after 10 years. Me is still me, chaos is still chaos, but both of us are different, carry certain geometrical phase, right? So, of course, I mean, this is basically to show you that not only 0 and 1, these kind of 2 spins in light that we can play with, but also we can play with the nonlinearity. So I will basically skip this one due to the time limitation, but it actually have a multiple dimension of degree freedom. So you can basically, out of the same pattern, you can basically shine upon this kind of a laser. So you can get 3 kinds of different, totally different choreographed images out of the same sample. 2 are on the fundamental frequency, the other one on the second harmonic generation. So you can also use frequency to help to multiplex your output. And this one basically is a very crazy idea to further combine with all the light spin and wavelengths, geometrical phases, the rotation angle optimization at different positions. So out of the same sample, we can generate 63 different holographic images out of one static sample. All right, so since we have touched upon a little bit like the face, so I would like to mention this kind of face formally. And in the past, basically, we say that now if you like this creature, you move around, then the face carries a pi difference. That's exactly what we want to play with. So this is a unit, all right? You have like structures, method structures, and we put a diode there. So diode with DC bias. So you can apply a DC bias or not applying that. So with and without it, the reflection wave carries a difference of pi phase difference. So to mimic this kind of go-around example. So now if I want to generate a certain hologram, whatever I want to generate, so you basically, you just program it in your computer, and the computer will tell you that at a certain position, you want to have it phase of 0 or pi. So you have two options, like a dice, or like a coin, you only have two sides. And basically, you can always program it, because at this particular position, let's say this position, I can apply the voltage, or I can remove the voltage using DC bias to change pi or 0 at this position in real time. So this metasurface behind actually has a lot of DC and voltage supply, and it's controlled by the FPGA to control. So it can, in real time, to generate unlimited holographic images as you wish. And clearly, you can see that the figure A on the right, you can clearly see the green light. That's actually the phase difference between the so-called on state and off state. So it's around 180 degrees. All right? So 180 degrees is the phase of pi. So EJ pi is -1. All right? So basically, we can show that tens of centimeters after this metasurface, and at this plane, we can, in real time, show all these letters in real time and changes by programming our FPGA. All right? But I think we need to be even more intelligent. So with this kind of infrastructure at hand, actually, we can design it to be a more so-called intelligent metasurface, really. So this one, we have to use certain training samples. Basically, we take a picture of the student, and then we use microwave to image. So basically, we can get the measurement, which is the y vector, and this is x is actually the position or the shape or the image you want to reconstruct it, which is unknown in real setup, right? But you have to train this matrix H first using the existing data. So we can do this one in a very easy way because now it's in microwave. So we can basically fill up this kind of matrix H. So once matrix H is established by this kind of a learning algorithm, and then next time, if just a stranger pass by and do whatever gestures, even though all the light is turned off, a microwave doesn't matter, right? Microwave can always image you, and then based on what we really measure in the y vector, we can take the H inverse and get the target's position images. So this is how the structure, this idea is implemented. So you can see that now we use a principal component analysis method. So we can basically train the system with different times. And you can clearly see that when the measurement numbers increases, there's a video. That's a cue for the hero backstage. So it moves. So once the measurement numbers is good enough, basically the microwave image is clearer. All right, that's good for the reconstruction. All right, given the time, I will skip it. But this is two video. Again, please play it for me, thanks. These two videos. So basically, after we train this setup, so the student will be standing there, carrying a scissor. And in real time, we can basically construct the microwave image. You can even see this kind of scissor, right? And since it's microwave, basically you can even hide behind a wall it doesn't matter because the microwave can penetrate anyway, as long as it's not metal, right? So it can also serve as a good way to do this kind of post-war imaging, even though you don't have the line of sight. And literally, I think we need to really enlarge the impact. So this is how we imagine. So you can basically design this kind of metasurface in the indoor environment, because then you can hide all the wires and the FPGA stuff in the wall. You don't see it, you don't bother. And then, of course, the source. In the previous example, actually, we have an antenna to send in the wave. But this one, we actually have another paper. I don't have the time to share, but we have a paper on light science applications. Basically, we use Wi-Fi's signal, because Wi-Fi is everywhere. So basically, you can do this kind of programming, and we can trace multiple targets, not just a single one. And even for a single one, we can actually image the wave to a region of interest, like your heart, your mouse. Actually, we have another paper to read your mouse, because you can just say something without voice, and we can basically let a wave through this wall, the metasurface wall, to focus to your lips. And then we can use microwave to read it, to image it, and use machine learning to tell what you are speaking. All right, so this is doable. It's already verified in experiment. And we have another paper that is in press. We even can use our eyes with a certain assistance from eyewear. Basically, if you move your eyeball, basically you can drive the UAV. You can drive the unmanned flying vehicle. All right. So that's very interesting stuff overall, and there's a lot of things going on. And eventually, we want to make everything wireless, really wireless, no wires, because still we need to use certain wires to apply DC voltage. So right now, we can use light direct to pattern, because then we have to solder certain light-sensitive elements, certain different kind of photodiode. So if the light comes in with a certain threshold limit, then this diode will be on. Below that, it's off. So you can use patterned light to control this kind of a metasurface. And this metasurface then generate the desired pattern of microwave. So that's how the sample looks like, and that's the setup. So you can use a structured light to control the beam shape. All right, so eventually we want to make it connected to people's brain, so we can try to use brainwave to control the metasurface. That's even crazier, right? But anyway, we have done certain very stupid proof of concept. So we buy certain stuff on shelf that is like Arduino setup. And this Arduino has very interesting and simple setup. You put a one sticker here and a two sticker here. And they have a certain method to record the score of attention. So of course, now we classify the attention into 4 levels. And these 4 levels is an orange curve. So it's like a 25%, then 50%, 75%, and 100%. So then it can output 4 kinds of voltage levels. And these 4 voltage levels is enough to drive a metasurface. And that's how the student looks like, right? A lady again, then she is just trying to focus and slightly defocus and completely defocus, gets kind of 4 level of input of voltages, and then because we can beam shape the microwave devices. And essentially, we have another work that is using a P300 brainwave signals to drive it further. I think if you are actually, I'm not a really P300 expert, but we know how to fuse with other experts. So we put an EEG helmet, and when you think about something, your P300, and if, let's say, the target image is flashing in front of your eyes, you have a P300 signal in your brain wave. I mean, why it calls 300 is kind of like the delay is 300 milliseconds. So you can clearly see that now at the 300 millisecond, you have a difference between the highlight and non-highlight signals. And we capture this one to serve as a control. And essentially, you use this kind of signal to control the FPGA, right? But now everything is without any wires. So this is 3 gentlemen. The top panel is to show that we can deliver certain text, like a hello world, based on 2 setup. And the below one is to use his EEG cap to to control the beam shape, all right? So I think I will not show the video to save some time. And I stuck again, but I think I'm almost done. So the next one is the optical angular momentum, as I showed before, about the golden ratio metasurface. So this is how we drive it to the extreme, because we can generate different kind of topological charge, which is orthogonal. So that's very important. When you talk about 0 and 1, or this kind of degree freedom, we want 2 or more orthogonal degree freedom so that you can mingle and match together, right? And then here is topological charge. Each one is orthogonal to each one. So then we also combine with polarization, and also combine with wavelengths, and combine with a spatial control. So you can generate very complicated dot array of different colors, different topological charges. And use a second sample to decipher it. So you can basically do a lot of this kind of so-called optical key and optical log thing out of the whole one sample, one platform. And we use this video to show that how fast we can use laser to pattern this kind of CVB unit. It's a 3D printing process, all right? It's a spiral faceplate with a little bit like rods on top. Okay, so I think I almost used my time with a little bit delay. I'm sorry for that, but I just quote my favorite quote. Pauling actually mentioned God made solids, but surfaces were the work of the devil. So basically, metasurface sounds like a meta-devil. And now the meta-devil becomes very intelligent. Quite scary, but interesting. So I think I talk about a lot of degree freedom, how to mingle things, degree freedom together. So since I'm from Oriental part of the globe, so I want to quote Tao Te Ching. So the Tao engendered 1, 1 engendered 2. Here, 1 and 2 means degree freedom, or the binary basis. 2 engenders 3, and 3 engenders many things. So if you want to read all these kind of things in a nutshell, you can refer to our review papers, so on and so forth, 3. And all our things up to 2022 are summarized there. And thank you very much for your attention.
Thank you very much, Professor Qiu, for the fascinating talk. I was very much amazed by the interdisciplinary nature and the width and the depth of your research. So now we have time for questions, and we have 2 microphones set up there. So if you have questions, please just walk to the microphone.
Hello, Professor. Thank you for your talk. I was reading up on metasurfaces, and I've seen some that are on VO2 or temperature-based that trigger that. So it was very interesting to me to see your research that you have some that are element-enabled. So in your experience, how do you determine what is the trigger for the metasurfaces to change its abilities?
Sorry. For the VO2 stuff, like a phase change material, of course, you have options to change the phase transition, right? Basically, they change the epsilon, for example, or conductivities. So, but VO2 has its limitation because the hysteresis group, when you go back and forth for a few times, I think it's going to be, it will not be exactly forming a digital metasurface per se, because the phase will no longer be that accurate. But of course, I mean, our application niche is in the microwave. So we use pin diode. That guy is pretty stable. After many times, like a DC bias on and off, it's still there. It's just like a through or cut off. So it's in metal sense. So I agree that basically it's, if you want to push it to the higher frequency, this kind of tunability is one issue. So far, I don't see a perfect way to solve this one. Yeah. So, but in microwave, that's how we can find a huge impact and ready applications, especially in the smart home, even the smart hospital. Because one of our application has been kind of like applied in a so-called personal ward. You can just lie on the bed, and everything can be turned off, and you have like a smart surface there in the wall, and they can trace you so-called region of interest, meaning you can see whether the guy is still there, false or not, and whether his heartbeat, his breath, everything can be focused into special places of your body. Yeah. So I mean, there's a trade-off anyway. So frequency-wise and application values. Yeah.
Okay. Much.
Hi, Professor. Thank you for your lecture. I'm a student major in wireless communication, and I'm excited to see you that you managed to eliminate the side loop and focusing the beam at the same time. And it's very beneficial to eliminate the side loop as the focus the beam. Could you explain more about how you managed to do these two things in the same time?
Yeah, so if you consider the usual focus wave, right? So basically you have different kind of wave, then it focused into a spot. That actually, you have to obey the diffraction law. Yes. So when you consider super oscillation method, which is initiated by Michael Berry, he proposed a certain structure that it can collect more high K components into the focal spot. But the high K component can interfere at a limited region, which results in a small, very sharp, tiny spot in the middle. But this one is below diffraction limit, but nothing is free. If you focus into that small spot, your power, your energy will be somehow like squeezed, pushed into the side band, the side band, the side ring. As you look at the amplitude, it's like the smaller the center beam you wish to get, the huger, the bigger side band energy you get.
The bigger radius.
Yeah, radius will also change, but also the power intensity will increase as well. So this is actually not good for imaging or for the scanning purpose. Because if you scan, even though the center spot is good, very small one, but you have a sideband, and all the scattered signals will be collected, so it will ruin your resolution eventually. So right now, we actually consider that from the traditional diffraction limited imaging to the super oscillatory imaging, it's not like a zero-sum game. Actually, there's a certain regime where if you push, you introduce a little bit higher K component into a certain boundary, all right? So it means that when you approach to this boundary, the central spot, the FWHM, actually doesn't improve further much. It almost close to the super oscillation counterpart. But if you really want to shrink like another 10 nanometer in terms of FWHM, the sideband grows rapidly. So why we have to enter this regime? We can just stay like this is a boundary, I just stay here. So I gain from the smaller center spot, and I avoid very huge sideband. So this is actually how we can optimize our optimization scheme in the design process to stop somewhere, to stop bringing more high K components, which doesn't really help. And they can actually ruin things, so kick them out.
Okay, thank you so much.
Just to follow up along that question, thank you for your talk. Is it possible to possibly, on the outside of the screen, put a different wavelength light, so like violet, which would allow the focus to be reduced to diffusion?
Because your purpose is
to create a synthetic wall that would allow the focus in the middle.
Yeah, but I think in our small community, some people use a certain pupil to do that. So, but the thing is, the efficiency of your light utilization is really, really bad, because this center spot, if you block the sideband, it's only like a few % of your input light. So literally, it's not that useful. So the best is not to be extreme, right? So you have to trade off between two things.
Okay, so as an outsider of the field, I have some naive general questions. you talk about the fusion of machine learning and AI and human brain control. To me, I think this is the future. But at the same time, since human brain control is very error sensitive,
Yes.
so you really need to control the error rate and make your AI part to be verifiable and safe per se. So could you share some opinions on how you can possibly do that?
Yeah. So for example, for the P300 version of the so-called brain-computer interface metasurface, we call it BCI metasurface, there's certain limitations. I mean, the limitation comes from the EEG helmet, because this is not a so-called minimum invasive method. If we really have certain small pins just to penetrate a little bit to your scalp, that's going to be very efficient, very, very efficient, because the signal that we collect is more accurate. But this kind of EEG is near-field coupling. So sometimes the EEG helmet simply doesn't work on certain tester because their head is not fitting well with the helmet. So that indeed brings a lot of error message. Second thing is, due to this kind of EEG helmet, the signal strength that the P300 is a little bit fuzzy. So we need this tester to be selected. So not everybody can be the tester, because you have to make sure that your P300 signal is good. So somebody is not good. So if you want to be the controller, using brainwave to control the microwave, beam shaping, or whatever imaging, you have to be the selected guy. So in terms of large-scale application, I think, of course, if you get this kind of guys, good enough. You don't let everybody, be the player. So I think so far because we control the microwave beam shaping, the accuracy is still okay. But let's say if you want to control certain more precise, like cutting or whatever, then possibly the algorithm needs to be more powerful. But that's beyond my scope. I cannot solve that part.
Yeah, thank you. And another question is, when you talked about artificial muscle, how artificial are they? Are they something like organoid? I mean, when I talk about artificial muscle, the most interesting part to me is the force feedback. Okay. So how can you achieve this kind of things?
We do it in a very low-ranked version of muscle. So we basically consider the extent of contract and expand this one. We don't have a feedback. So of course, I mean, if you put a little bit sensor there, you can get a feedback, but we don't have this part. So we just consider how we can expedite this kind of contract and restoration. So that's why we need to consider certain material that has a very weird dependence on the expansion and the contraction. And then we find graphene oxide is a very interesting material. And then it is still not enough, because it takes a long while to accumulate this kind of morphology. Then we put certain plasmonic nanoparticles to inject into the joint area. So when the light impinges upon this joint area, the localized plasmon resonances will speed up the heating process quite a lot. So the force will be, the contraction force will be larger, faster. Yeah, yeah. But so far it doesn't come with a feedback loop. Yeah, yeah. Nice. But it's a good suggestion that we should consider that later on.
Thank you. Any other questions? Okay. So if no more questions, let's thank Professor Qiu again for the wonderful talk. Yeah, so that concludes the keynote session for today. Okay. Thank you.